Traveling at the speed of light through the cosmos. Chapter 1. Push-off. What the speed of light really means. There is a number in nature so important, so unyielding, that it shapes the very fabric of reality. It is not just a speed, not just a measure of distance divided by time. It is the speed limit of the cosmos itself. Tonight, we are going to ride it. The speed of light. Part 1. The definition of c. In physics, we symbolize this constant as c. It is exactly 299,792,458 meters per second in vacuum. Not approximately, not give or take, exact. Since 1983, the meter itself, the most basic unit of length in the international system, has been defined in terms of light's travel in a fraction of a second. In other words, when you measure distance, you are secretly measuring light's footsteps. This is how deeply the speed of light is woven into our understanding of reality. It is not just a number sitting in a textbook. It is the ruler and the stopwatch of the universe. Part 2. Everyday consequences. Think about this. The moment you step outside and feel the warmth of the sun on your face, you are actually feeling the past. Those photons left the solar surface 8 minutes and 20 seconds ago. You are never interacting with the present-day sun. You are seeing its history, slightly delayed. When astronauts on the moon spoke to Houston in 1969, every "Roger that" and "the Eagle has landed" carried a 1.3-second delay, because that is how long it takes light and radio waves riding it to cross the 384,000 kilometers separating Earth and Moon. Scale this up. Signals to Mars can take anywhere from 4 to 24 minutes, depending on orbital positions. To Pluto, hours. To the Voyager probes, humanity's farthest emissaries, over 22 hours one way. In cosmic terms, even our own neighborhood is not instant. The universe speaks slowly, and light is the courier. Part 3. Why light has a speed limit. Why can't anything outrun light? To understand this, we need to step into Einstein's theory of special relativity. It tells us, the faster you go, the more energy it takes to keep accelerating. Push an object with mass closer and closer to c, and the required energy grows toward infinity. Infinity is unreachable. Nature has built a brick wall here. But it is not just energy. Time itself behaves differently. If you could somehow hitch a ride at near light speed, your clock would tick more slowly compared to clocks back home. Your body would age less. Distances in front of you would shrink. Einstein's insight was this: the universe reshapes time and space to preserve c as the same for everyone, everywhere. Whether you're standing still, flying at 99% of light speed, or riding a photon itself, c does not budge. Part 4. Light as a time machine. Now, imagine the night sky. Every star you see is not shining now, but in the then. The closest star system, Proxima Centauri, is 4.25 years away at light speed. The light we see tonight left that star around 2019. Look at the Andromeda Galaxy, visible as a faint smudge with the naked eye on a dark night. You are seeing it as it was 2.5 million years ago. Humanity did not exist when that light began its journey. Look deeper, with telescopes like Hubble or James Webb, and you see galaxies billions of light-years away. Their light began its journey when Earth was still molten, or when life was just beginning in our oceans. The night sky is a living museum of cosmic history. Each photon is a messenger, carrying a story from a different chapter of the universe. Part 5. A universe measured in light. Because light is so fundamental, astronomers often abandon kilometers altogether. Instead, they measure distance in light seconds, light minutes, and light years. The Earth-Moon gap? 1.3 light seconds. Earth-Sun distance? 8.3 light minutes. To Neptune? About 4 light hours. Across our Milky Way galaxy? Roughly 100,000 light years. Using light as a yardstick instantly reminds us of the vastness of cosmic scales. It's as if the cosmos itself only agrees to be measured in its own currency, the travel time of light. Part 6. Expansion Break for Pacing. Take a moment to look around your room. Every object, your screen, your chair, even your own body, is made of atoms that once absorbed or emitted light. Every electron in those atoms interacts with photons. The fact that you can see me, hear me, or watch a rocket launch across the world depends entirely on this universal speed limit. Light connects us not just across space, but across time. Part 7. The dual nature of light. So far, we've treated light as a simple traveler, a particle moving at speed c. But light is also a wave. It oscillates in electric and magnetic fields, which is why it is part of the electromagnetic spectrum. That spectrum stretches from gamma rays and X-rays through visible light into microwaves and radio waves. They all move at c in vacuum. The only difference is their wavelength and energy. This is why your microwave oven, your Wi-Fi router, your favorite radio station, and the glowing colors of a sunset are all the same thing. Light, wearing different disguises. Part 8. The human connection. And here's the most poetic part. You yourself are made of light. The elements in your body, carbon, oxygen, iron, were forged in stars by nuclear fusion, a process that releases light. The sun still shines today because it turns hydrogen into helium, releasing photons as byproducts. Those photons scatter through its dense interior, taking thousands of years to escape. The sunlight you feel this morning may have begun its random walk before human civilization even existed. To travel at light speed, then, is not just to move quickly, it is to trace the very heartbeat of the cosmos. We have just stepped onto our vehicle, the speed of light itself. We have defined it, measured it, and glimpsed its consequences. In the next chapter, we will ignite the engines of relativity and discover how time and space warp when we approach this universal limit. If light is the ruler of the cosmos, relativity is the law that explains why. Chapter 2. Relativity on the dashboard, time dilation, and length contraction. The closer we get to light speed, the stranger reality becomes. Our vehicle doesn't just go faster, it reshapes time, space, and even the way we perceive the universe. Part 1. Time runs differently. Imagine two twins. One stays on Earth. The other boards a spaceship that accelerates to 99% the speed of light. For the traveler, only a few years pass on their onboard clock. But when they return home, their twin has aged decades. This is the famous twin paradox, a direct result of time dilation. Time dilation isn't science fiction. We measure it daily. Astronauts aboard the International Space Station orbit at about 7.7 kilometers per second. Their clocks tick microseconds slower per day compared to clocks on Earth. It's tiny, but real. Our GPS satellites must correct for both special relativity, because they're moving fast, and general relativity, because they're farther from Earth's gravity. Without these adjustments, your phone's map would drift by kilometers every day. Part 2. Length contracts. Now, imagine you're the traveler. From your point of view, distances compress. A star 10 light-years away might feel much closer, perhaps only 2 or 3 light-years in your contracted frame. To you, the trip takes a few years. To Earth observers, it takes a decade. Both are correct in their own reference frames. This is the magic of special relativity. The universe bends its measurements to preserve the speed of light. No matter how you measure, c is constant. Part 3. The energy barrier. But why can't we just go all the way, to 100% of light speed? Here's the catch. As you accelerate, your relativistic mass effectively increases. It's not that you gain mass, but that more and more energy is required to keep pushing you. Approaching c, that energy curve shoots upward to infinity. Nature has placed a cosmic speed limit. This doesn't mean fast travel is useless. Even at 99.9% of c, time dilation is so extreme that you could traverse interstellar distances in what feels like a short personal time span. The cost is simply that thousands of years pass for those left behind. Part 4. What you'd see. Perception itself changes. Stars seem to bunch up in front of you, creating a brilliant forward cone of light. Ahead, their colors shift bluer, more energetic. Behind you, the cosmos fades red and dim. The faster you go, the narrower your forward view becomes, almost like a cosmic tunnel vision. Scientists call this relativistic aberration. Combine it with Doppler shifts, and the sky becomes a kaleidoscope of distorted starlight. Simulations show how surreal this view would be. Space itself feels bent, even though it's your frame of reference doing the bending. Part 5. Living at light speed. What would life be like for a traveler? Inside the ship, normal. Your coffee still steams, your heart still beats, your music plays at the right tempo. Physics works as usual in your local frame. Only when you compare notes with someone outside, someone stationary, does the weirdness emerge. This is relativity's lesson. Motion is relative. No absolute frame of rest exists. The only invariant is c, the speed of light. Everything else adjusts to make sure that law holds. Time dilation, length contraction, and the energy barrier. These are not obstacles, but invitations to see reality differently. We have strapped ourselves into a relativistic dashboard. Now let's take it for a ride. Outward from Earth at the speed of light. Chapter 3. Outbound from Earth. 8 minutes to the Sun, seconds to the Moon. We've launched. Let's see what traveling at the speed of light actually feels like, step by step, across familiar territory. Part 1. The first leap. Earth to the Moon. Just 1.3 seconds after departure, we've already passed the Moon. Think about that. A journey that took Apollo astronauts 3 days, light covers in barely more than a single heartbeat. The Moon, our silent neighbor, is suddenly a memory behind us. Part 2. The solar furnace, Earth to Sun. Keep going. In 8 minutes and 20 seconds, we reach the Sun. Look closely. Its seething surface is a storm of plasma with convection cells the size of continents. Magnetic fields twist and snap, releasing flares and coronal mass ejections. Yet all of that brilliance is 8 minutes old to us on Earth. We never see the Sun live. Imagine pausing here. If the Sun were to vanish suddenly, an impossibility, but imagine. Earth would orbit happily in darkness for over 8 minutes before gravity and light stopped arriving. Part 3. The inner solar system. Beyond Earth, Mercury orbits in just 3 minutes light time from the Sun. Venus, about 6 minutes. Mars, around 12 minutes depending on position. Already the scale of time is stretching. To communicate with a rover on Mars, scientists must send commands and then wait up to 24 minutes for a reply. The conversation lag of light. For missions like Perseverance, autonomy is key. The rover must think for itself because waiting for Earth's response would take too long. Part 4. The Outer Giants. Now accelerate outward. At light speed, you pass Jupiter in about 35 minutes. Saturn comes into view after about 1 hour and 10 minutes. Uranus appears at 2 hours 40 minutes. Neptune at nearly 4 hours. For comparison, the Voyager probes, launched in the 1970s, took years to cross these distances. Voyager 2 needed more than a decade to reach Neptune. At light speed, you do it in the time it takes to binge-watch a season of your favorite show. Part 5. The Kuiper Belt and Beyond. Beyond Neptune lies the Kuiper Belt, a ring of icy debris, dwarf planets like Pluto, and countless comets. Crossing it takes another 5 to 6 hours. Here, light still reigns supreme. But we are approaching the Sun's frontier, where its influence weakens and interstellar space begins. Part 6. The Human Perspective. Think about the scale we've just crossed. In one workday, 8 hours, light has traveled from the Earth, past the giant planets, and into the icy wilderness beyond Pluto. What humanity achieves in decades, light accomplishes in a single shift. And yet, the nearest star still lies more than 4 years away. We've barely scratched the surface. We've left the Earth behind and crossed our solar system in hours. In the next stage, we will breach the Sun's protective bubble and venture toward the interstellar sea. Chapter 4. The heliosphere's shore, past the heliopause. We are leaving home waters now. Beyond the planets, beyond Pluto's cold orbit, lies a vast invisible bubble. It is the Sun's frontier, the heliosphere, our cosmic shoreline. Part 1. What is the heliosphere? The Sun is not just a light bulb in the sky. It is a nuclear engine, constantly throwing out a stream of charged particles known as the solar wind. These particles race outward in all directions, inflating a bubble around the Sun. That bubble, the heliosphere, is our protective cocoon against the harsher particles of interstellar space. Inside it, the Sun dominates. Its magnetic field stretches far, shaping the paths of cosmic rays. Outside, the galaxy takes over. The edge is not sharp, but layered, like the foam of waves breaking on a beach. Part 2. The termination shock and heliopause. First comes the termination shock. Here, the solar wind slows as it rams into the thin gas of the galaxy. Beyond that lies the heliosheath, a turbulent zone where solar and galactic particles mingle and swirl. Finally, at the outermost edge is the heliopause. This is where the Sun's influence yields entirely to interstellar space. Crossing it is like stepping off the continental shelf into the open ocean. There is no marker, no signpost, but the change is profound. Part 3. Voyager, humanity's ambassadors. 2 tiny spacecraft, launched in the late 1970s, have carried us across this boundary. Voyager 1, launched in 1977, crossed the heliopause in 2012. Its twin, Voyager 2, followed in 2018. Both now drift in the interstellar medium, still whispering faint signals back to Earth after more than 4 decades. Their instruments told us what theory only guessed. The density of particles rises beyond the heliopause. Magnetic fields change direction, and the Sun's shield no longer dominates. These spacecraft are our message in a bottle to the galaxy. On board are golden records, phonograph discs etched with sounds and images of Earth. Greetings in dozens of languages, music from Bach to Chuck Berry. A map pointing back to our Sun. Someday, perhaps, someone will find them. Part 4. Light speed across the heliosphere. At light speed, this entire journey is swift. From the Sun to the termination shock takes about 14 hours, to the heliopause about 17 to 18 hours. A single day of light travel carries us outside the Sun's protective bubble, something the Voyagers took decades to achieve. Imagine pausing here. Behind you, the solar system glows faintly, planets circling, comets drifting, the Sun still a bright star. Ahead is true interstellar space, thin, cold, and ancient. Part 5. What lies beyond. Outside the heliosphere, the interstellar medium rules. It is not empty, far from it. There are stray hydrogen atoms, dust grains, and magnetic fields twisting through vast reaches. On rare occasions, a supernova shockwave or interstellar cloud sweeps through. Stars orbit within this sea like islands in an endless archipelago. This is the galaxy's domain. We have stepped off our sun's porch and onto the galactic street. We are still close to home by galactic standards, but already we have left the sun's shield behind. Next stop, the nearest star, Proxima Centauri. Just 4.25 years away at the speed of light, a blink to photons, but a gulf for us. Chapter 5. First stars on the horizon, Proxima Centauri at 4.25 light-years. Beyond the heliopause, the first real landmark on our journey is the nearest star system. A small red sun flickers on the horizon, Proxima Centauri. Part 1. The distance to our neighbor. The Alpha Centauri system lies 4.25 light-years from us. That means light, traveling at nearly 300,000 kilometers per second, takes more than 4 years to cross the gap. For comparison, in that same time, Voyager 1 has traveled only about 0.002 light-years. At human speeds, the journey is almost unimaginable. Proxima is the closest of the 3 stars in the system. Alpha Centauri A and B, a binary pair, shine brighter, but they are a little farther out. Proxima is a faint red dwarf, invisible to the naked eye, but famous because it is ours in the cosmic sense, the nearest stellar neighbor. Part 2. A red dwarf star. Red dwarfs like Proxima make up about 70% of the stars in our galaxy. They are small, cool, and dim compared to the Sun. Proxima's mass is only about 12% of the Sun's, and it shines 500 times less brightly. If placed next to the Sun, it would look almost like a dying ember next to a bonfire. Yet red dwarfs are survivors. They burn their fuel so slowly that they can live for trillions of years, far longer than our Sun's projected 10 billion-year lifespan. In the far future, when the galaxy is old and dim, red dwarfs like Proxima will still glow. Part 3. Planets of Proxima. Proxima Centauri has at least 2 confirmed planets. The most intriguing is Proxima b, discovered in 2016. It is roughly Earth-sized, orbiting in the star's habitable zone, the region where liquid water could exist. At first glance, it seemed a perfect candidate for life. But reality is harsher. Proxima is a flare star. It frequently blasts its planets with intense bursts of radiation. A world orbiting so close may struggle to hold on to its atmosphere. Still, the discovery ignited imagination. If we ever send probes to another star, Proxima b will be the first target. Part 4. Lightspeed Journey to Proxima. At light speed, the trip takes 4.25 years. Let's imagine riding that photon. Behind us, the Sun shrinks to a brilliant dot. Ahead, Proxima grows from invisibility into a faint red glow. Stars around us seem frozen, barely shifting. Even at sea, the galaxy is so vast that most constellations hold their shape for millennia. Pause for a moment. you are 4 years into your journey. On Earth, politics have shifted, new technologies have been invented, and perhaps a new rover has landed on Mars. For you, no time has passed. Light simply moves. Part 5. Why nearest still means distant. 4 light years may sound small, but it is enormous by human standards. The fastest probe we have ever built, Parker Solar Probe, reaches about 700,000 kilometers per hour, blistering by spacecraft standards. At that speed, it would still take over 6,000 years to reach Proxima Centauri. This is why light remains our only viable vehicle in thought experiments. For now, even our dreams of interstellar travel, like fusion rockets, solar sails, or antimatter drives, are just that, dreams. We have touched another star. From here, the galaxy itself opens. The Milky Way stretches 100,000 light-years across, a sea of hundreds of billions of suns. Our next step is to cross it, at light speed. Chapter 6. Crossing the Galactic Sea, 100,000 light-years of the Milky Way. We have left our sun behind. Ahead lies an ocean of stars, the Milky Way, our home galaxy, 100,000 light-years wide, hundreds of billions of suns, countless worlds, nebulae, and mysteries. This is our galactic sea. Part 1. Structure of the Milky Way. The Milky Way is a barred spiral galaxy, meaning its core is shaped not as a perfect sphere, but as a glowing bar of stars. From that bar extend spiral arms, great curling rivers of light. Our solar system resides in a minor arm called the Orion Arm, about 26,000 light-years from the galactic center. If you could see the galaxy face on, it would resemble a pinwheel. But from Earth, embedded within it, we see it edge on, a hazy band of light stretching across the night sky. That band is the combined glow of millions of stars too distant to see individually. Part 2. The scale of the journey. At the speed of light, crossing the galaxy from end to end would take 100,000 years. That means if you set off at sea when humanity was still painting on cave walls, you'd only now be arriving at the opposite shore. Even though we've reached another star, we are still trapped in a single island of space. The distances are staggering, and yet this is only one of billions of galaxies. Part 3. The Galactic Center. At the heart of the Milky Way lies a monster, Sagittarius A star, a supermassive black hole about 4 million times the mass of the Sun. It lurks behind clouds of dust and gas, invisible in visible light, but blazing in X-rays and radio. Stars near it orbit at incredible speeds. Some complete an orbit in mere decades, proof that something immensely heavy is hiding there. These stellar whirls are the evidence that confirmed our black hole's existence. Pause here. Imagine approaching it at light speed. You'd see stars whip around like fireflies caught in a whirlpool. But beware. Closer in lies the event horizon, a point of no return, even for light. Part 4. Star nurseries and graveyards. Scattered throughout the spiral arms are nebulae, vast clouds of gas and dust. Some are stellar nurseries, like the Orion Nebula, where gravity compresses gas into new suns. Others are remnants, like the Crab Nebula, the ashes of a star that exploded centuries ago. Traveling at light speed, you would pass through these regions as ghostly curtains of color and dust. Each one tells a story: birth, life, and death of stars. Part 5. Globular clusters and halo surrounding the Milky Way. Is a halo of globular clusters, dense swarms of ancient stars, among the oldest objects in the galaxy. These clusters are fossils of galactic history, relics from when the Milky Way was still forming. Light-speed travel lets us skim past them in seconds, yet each cluster contains hundreds of thousands of stars, each potentially with planets, each with its own stories. Part 6. The Human Perspective. Pause for scale. A human lifetime, maybe 80 years, is not even a blink compared to a light-speed crossing of the Milky Way. And yet, we can map it. We can picture it. Through telescopes and surveys, we know where we live. This is our galactic address: Earth, Solar System, Orion Arm, Milky Way Galaxy. A cosmic ID card, written in light. We have crossed the Milky Way in imagination, at light speed. But galaxies themselves are not static islands. They drift, collide, and, most importantly, they recede. Because the universe itself is expanding. That is our next journey. Chapter 7. The Universe Flows, Redshift and the Expanding Fabric. The farther we travel, the more we notice something strange. Galaxies are not fixed, they are flowing away from us. The universe itself is stretching, carrying them outward like dots on an inflating balloon. Part 1. The Discovery. In the 1920s, astronomer Edwin Hubble studied distant galaxies. He found their light was shifted toward the red end of the spectrum, a phenomenon called redshift. The farther away a galaxy was, the greater its redshift. This simple observation carried a profound meaning. The universe is expanding. Space itself is stretching, and galaxies are carried along like corks on a river. Part 2. Redshift explained. Light behaves like a wave. When the source moves away from you, its waves stretch, lowering their frequency, just like the sound of a siren dropping in pitch as it drives past. For galaxies, this stretching shifts light toward the red. But unlike a police car moving through space, galaxies aren't just racing away from us through static emptiness. It's space itself that is expanding. Galaxies are being carried apart by the fabric of the cosmos. Part 3. The Hubble-Lemaitre Law. The relationship is simple. The farther a galaxy is, the faster it recedes. This is the Hubble-Lemaitre Law. Measure the redshift, and you can calculate distance. It turns the night sky into a 3D map. From this law, astronomers estimate the age of the universe. By running expansion backward, we reach a beginning, about 13.8 billion years ago, the moment of the Big Bang. Part 4. What expansion looks like at light speed. Traveling at light speed through this expanding fabric is disorienting. Galaxies ahead seem to drift away faster the farther you look. Some are receding so quickly that their light is stretched beyond visible wavelengths, into infrared or even radio. The James Webb Space Telescope peers into this stretched light, capturing galaxies from when the universe was less than 1 billion years old. Their faint red glows are whispers from the dawn of time. Part 5. Cosmic Implications. Expansion reshapes our destiny. Galaxies bound by gravity, like Andromeda and the Milky Way, will merge. But most galaxies will drift farther and farther away. Someday, distant observers will see only their local group, the wider universe hidden beyond their horizon. This isn't just abstract theory. The very fact that we can see billions of galaxies today is a privilege of living in a young, transparent universe. Part 6. Human-Scale Analogy. Imagine ants painted on a balloon. As the balloon inflates, each ant sees all others moving away. None is special. All share the expansion. This is our universe. No center, no edge, just space stretching everywhere at once. At light speed, we surf this expansion. But no matter how fast we go, we can never outrun it. The universe is not static. It flows, it stretches, it carries galaxies with it. In our next step, we will travel back to the very beginning of light itself, the cosmic microwave background, the oldest light we can see. Chapter 8. The oldest light you can see, the cosmic microwave background. As we journey deeper into the past at the speed of light, the galaxies thin out. Stars disappear. Eventually, we reach a horizon not of distance, but of time. Here lies the oldest light you can ever see, the cosmic microwave background. Part 1. The Young Universe. Wind the clock back to 380,000 years after the Big Bang. The universe is young, hot, and dense. Matter and light are entangled in a cosmic fog. Photons scatter endlessly off free electrons. Space is opaque, like trying to shine a flashlight into milk. But as the universe expands, it cools. At about 3,000 Kelvin, electrons settle down, binding to protons to form neutral hydrogen. Suddenly, the fog clears. Light can finally stream freely across space. This great release of photons is what we call the cosmic microwave background, or CMB. Part 2. A baby picture of the universe. The CMB is everywhere. No matter where you point a radio telescope, you detect this faint microwave glow. It is the afterglow of creation, stretched from visible light down to microwaves by billions of years of cosmic expansion. In the 1960s, two radio engineers, Arno Penzias and Robert Wilson, stumbled upon it by accident. They were puzzled by a persistent hiss in their antenna, one they even tried to blame on pigeons nesting inside. But it was not noise. It was the echo of the Big Bang itself. Their discovery won the Nobel Prize. Part 3. Mapping the tiny fluctuations. To the naked eye, the CMB looks uniform. But satellites like COBE, WMAP, and Planck have mapped it in exquisite detail, revealing minute fluctuations, differences of 1 part in 100,000. These tiny ripples are crucial. They are the seeds of all structure in the universe. Galaxies, clusters, and superclusters grew from these slight density differences, amplified by gravity over billions of years. Part 4. What it tells us. From the CMB, scientists measure the age of the universe, 13.8 billion years, its composition, about 5% normal matter, 27% dark matter, 68% dark energy. Its geometry, nearly flat, meaning parallel lines stay parallel across cosmic scales. The CMB is not just a pretty picture, it is a blueprint of the cosmos. Part 5. Experiencing the CMB at light speed. Traveling at light speed into the past, you would eventually reach this great wall of light. Beyond it, no photons can carry information to us. It is not the edge of the universe, but the edge of visibility. The curtain of the CMB blocks our view of earlier times. What lies before 380,000 years? We must turn to neutrinos, gravitational waves, and theory. But with light alone, the CMB is our horizon. We have touched the oldest light, the universe's baby picture. But even this is not the ultimate barrier. Ahead lies a deeper mystery. Horizons. Not walls of matter, but walls of time, set by the very expansion of the cosmos. Chapter 9. Horizons and Limits. Why some galaxies are forever out of reach. The universe has no edge, no wall, no boundary you can touch, and yet there are limits. Not because of objects in the way, but because of time, expansion, and light itself. These are the horizons of the cosmos. Part 1. The Observable Universe. The universe is 13.8 billion years old. That means the farthest light we can see left its source 13.8 billion years ago. But because space has been expanding while that light traveled, the farthest galaxies are now about 46.5 billion light-years away in co-moving distance. This is the observable universe, a sphere centered on us, 93 billion light-years across. It's not that the universe ends there. It's simply the limit of what we can see, the region from which light has had time to reach us. Part 2. Particle horizon versus event horizon. There are two main horizons to understand. The particle horizon. Everything we can see now, limited by the age of the universe. The event horizon. Everything we will ever be able to see in the future. Because cosmic expansion is accelerating, galaxies beyond a certain distance will never send light that reaches us, no matter how long we wait. Their signals are forever cut off by the stretching of space. Part 3. A tragic consequence. This means most galaxies are slipping away, destined to disappear from view. Already, many are so redshifted that only the most sensitive instruments detect them. In trillions of years, distant observers in the Milky Way, or its future merged form with Andromeda, will see only their local group. The wider universe will be lost, hidden beyond horizons. We live at a fortunate time, early enough to still see billions of galaxies, but late enough that the cosmos has cooled, expanded, and formed structure. Part 4. Why horizons exist. The reason horizons exist is simple, yet profound. Light travels at a finite speed, and space itself stretches. The combination sets boundaries on causality. What can ever affect what? In physics, horizons are not metaphors. They are real, measurable limits on communication across the cosmos. Part 5. Traveling at light speed and meeting horizons. As a photon, you would never feel horizons. You simply travel until space expansion outruns you. To human minds, this is harder to grasp. Imagine swimming in a river whose current grows faster the farther you go. At some point, no matter how strong you swim, the current drags you back. That is the cosmic event horizon. At light speed, you can visit only a fraction of the universe. Vast regions remain forever out of reach, locked beyond the accelerating expansion driven by dark energy. The horizons of the cosmos remind us, the universe is not infinite for us. Its size, its story, its future, all are filtered through light and time. In our final chapter, we will ask, what would you truly see with your own eyes if you traveled at the speed of light through this endless night? Chapter 10. What you'd see near light speed, blue shift, aberration, and the strange. Traveling at the speed of light is not just fast, it is a transformation of perception itself. Space does not look the same. The universe warps in your eyes, bending light, shifting colors, compressing reality into the unfamiliar. What would you see? Part 1. Relativistic aberration, the forward cone. As your speed climbs towards C, stars no longer appear scattered evenly across the sky. Instead, they bunch together in front of you. This is called relativistic aberration. From your perspective, the whole cosmos seems to collapse into a bright forward cone of light. Behind you, stars stretch away, dimming into darkness. It is not that they vanish, but their light is bent forward by the geometry of space-time. It feels like tunnel vision, as if the universe itself is rushing toward your windshield. Part 2. Doppler shifts. Blue shift ahead, red shift behind. Now, look at the colors. The light from stars ahead grows bluer and more energetic, a blue shift. Radiation shifts upward in frequency. Ordinary starlight may blaze into ultraviolet, X-rays, or even gamma rays. Behind you, the opposite occurs. The light stretches redder and dimmer. Stars fade into the infrared, then into radio waves. until the rear universe disappears altogether from visible sight. Your perception of color becomes unrecognizable. The human eye, tuned to narrow bands of visible light, would see little but darkness ahead, unless aided by instruments that can detect higher energies. Part 3. Terrell-Penrose rotation. Why objects don't flatten. Here is a counterintuitive twist. You might expect objects to flatten, squashed in the direction of motion. But relativity produces something subtler, the Terrell-Penrose rotation. Instead of a pancake effect, objects appear rotated. A sphere zooming past you still looks like a sphere, but shifted, its far side strangely visible. This happens because the light from different parts of the object reaches you at different times. Vision itself is warped by the finite speed of light. At near sea, even your sense of geometry unravels. The world looks rotated, not crushed. Part 4. Light and the human senses. At these speeds, your eyes would be overwhelmed. Ahead, radiation surges into dangerous levels. Without shielding, the oncoming blue shift would fry your vision, even your DNA. Behind you, darkness would creep in. You would feel isolated in a bright tunnel of deadly light. To truly see at light speed, you would need instruments that translate invisible wavelengths back into human vision. Cameras that paint gamma rays as blue, radio waves as red. Only then could you reconstruct a coherent picture of the distorted universe. Part 5. Philosophical perspective. What would it feel like? Perhaps like falling endlessly into a tunnel where the past stretches away and the future blazes ahead. You are caught in a paradox, moving infinitely fast in one sense, yet frozen in another. Because for light itself, time does not pass. From a photon's perspective, if it had one, the moment it is born and the moment it is absorbed are the same instant. Distance collapses, time vanishes. The journey is instantaneous. So when you imagine traveling at light speed, you are imagining something fundamentally alien, not just fast, but outside time itself. We have seen the tunnel vision of aberration, the violent blue shift of starlight, the fading red behind us, and the strange rotations of geometry itself. Traveling at the speed of light is not only impossible for matter, it is unimaginable for our senses. Yet through physics, we glimpse its beauty and its terror. Epilogue. The rhythm of light. We began with a simple truth. The universe has a speed limit. Light, moving at 299,792 kilometers per second, binds space to time and past to present. From the Earth to the Moon in seconds, to the Sun in minutes, across the Milky Way in 100,000 years. Light is the universal courier of information, of causality, of history. We have surfed this limit across scales, past the Sun's protective bubble, to the nearest star, across our galaxy, through the expanding universe, to the oldest light of the cosmos, to horizons we can never cross, and finally, into the strange distortions of perception itself. The speed of light is not just a number, it is a law, a rhythm, a reminder that we live in a universe of limits, and within those limits, infinite stories unfold. Every sunrise is 8 minutes old. Every galaxy is a time capsule. And every glance at the night sky is a journey through the history of everything. We may never ride a beam of light, but in understanding it, we ride something greater, the wonder of the cosmos itself.